All right, now we need to go ahead and calculate some of these properties based on the information that's given and the fact that we have located the state, and this is the state that we are looking for. So the first thing is to determine the humidity ratio omega, okay? And we know that the humidity ratio omega is given here on the y-axis. So these values here that you can see, these correspond to the humidity ratio, okay? And these are given in terms of grams per kilograms of dry air. Okay, so normally we would want to keep the same unit. So what we're going to do is we're going to take the number and then divide it by 1,000 so that it's kilogram of moisture by kilogram of dry air. So the first thing that we need to do is get the omega for this point, and it's very straightforward. You just have to draw a horizontal line on towards this axis for omega. So you just draw a straight line, and it matches somewhere here. So that would be 14 gram per kilogram of air, or 0.014 kilogram of water per kilogram of air. Now it's slightly above 14 if you want to look at it. So to be more specific, it could be 0.0142, or if you just want to look up and write, even anything as 0.014 kilogram of water per kilogram of air is acceptable value. So that's how you get omega. Now about H, which is the mixture enthalpy, you just need to draw a line parallel to the enthalpy lines, which are these lines. This is for 80, this is for 60. And you see that this value is pretty close to 70, but slightly higher than 70. So if you look at it closely, you see that it's about 71.5 kilojoule per kilogram of air. Okay, so that's the enthalpy now. Now for the wet bulb temperature, we have to use the wet bulb axis. So this is the axis corresponding to the wet bulb temperature, which matches up with the line, with the saturation line corresponding to phi of 100%. And we can see there are these dotted lines indicating lines of constant wet bulb temperature. Okay, so you have 20 here, 21, 22, 23, and then 24 here. So the value for the wet bulb temperature, if you draw a line straight away, which is perpendicular to this axis, you'll see that it matches with the value for 24. Okay, so that's what we have for the wet bulb temperature. We also need to determine the dew point temperature and the volume. So for the dew point temperature, we just need to follow the same procedure we discussed before. That is, you start from the point of interest, then you keep on decreasing the temperature at the same value of omega, such that you reach the saturation line. Okay, once you reach the saturation line, you just need to draw a vertical line downwards. That's going to give you the dew point temperature. So when you do such a thing, when you draw a vertical line from here downwards, it goes and it matches up with the dry bulb temperature axis somewhere below 20 degrees Celsius, between basically 19 and 20. So you can, if you look at it more carefully, it's 19.4, but anything like 19.3 to 19.6 is acceptable as a value for this. Okay, so that's almost everything done. We just need to look at the volumes. Now, in terms of the volumes, there are also lines for constant volumes. You can see this is the line corresponding to volume of 0.9 meter cube per kilogram of dry air. This is for 0.92. These are the lines that I'm talking about. All right, and for our particular case, the point is here. So we're looking at lines which are parallel to 0.88 and 0.9. It's sort of somewhere between the two, and slightly more than 0.89, right? And if you look again, just by adjustment, you can sort of take it as it's not exactly halfway between 0.89 and 0.9. It's sort of closer to 0.89. So it's 0.893 is a more appropriate value. Again, this is a value you're picking up from chart. So 0.892 to 0.896 is all acceptable as the value for the volume. And remember, as we mentioned before, this is the volume for dry air or the vapor, okay, per unit kilogram of dry air. It is not the volume for the mixture. Okay, so that's the part of problem one done. Now you can have different types of psychrometric charts which have the same x and y axis but different units, like the ones that we have seen here. Now this chart is not given in your textbook. This chart is given in another textbook, or it can be found in typical industry guides. Now we can also look at the other way in which the psychrometric chart can be drawn, and we're going to look through another example to see what could be the other variation for psychrometric chart. All right, so let's look at this example. This is the psychrometric chart that you have in your textbook. This is actually figure A9, and here we have been told to use the figure and determine relative humidity, humidity ratio, and mixture enthalpy. The dry bulb and wet bulb temperatures are given as 30 degrees Celsius and 25 degrees Celsius respectively. Now, in the previous example, you had exactly the symbols given to you, but this is not going to be the case always, right? You got to know what relative humidity stands for. And from our understanding, we know that relative humidity has the symbol phi, okay? Humidity ratio is omega, and the mixture enthalpy is H. And these are what we are looking for. Now, we have been provided the dry bulb temperature as 30 degrees Celsius, the wet bulb temperature as 25 degrees Celsius. Again, we see that the wet bulb temperature is smaller than the dry bulb temperature. So we know for sure that the relative humidity is going to be lower than 100%. We don't know how low, but surely lower than 100%. So now let's look at this chart in a zoomed in view and try to understand how do we get that. The first aspect is to locate the point that we're looking for, right? Locate a point that has a dry bulb temperature of 30 degrees Celsius and a wet bulb temperature of 25 degrees Celsius. So when we talk about the dry bulb temperature, we're going to look at this axis right here, and we're looking at a dry bulb temperature of 30 degrees Celsius. So that's right away here. Okay. So you draw a straight vertical line along this path. Now we need to also identify the line with a wet bulb temperature of 25 degrees Celsius. So this axis corresponds to the wet bulb temperature, as you can see, wet bulb or saturation temperature, and you have 30, 20, and we're looking at somewhere in between, right? So we're looking at 25 degrees Celsius. So that basically corresponds to, if you count from here, it's 21. So these are slightly offset from the constant enthalpy lines, but parallel to the constant enthalpy lines. 21, 22, 23, 24, 25. Okay, so these are the lines that we're looking at, and this is the 25 degrees Celsius wet bulb temperature line that we need. So you just draw a line straight away. And this is our point. This is the point that we are looking for. Let me put that with green. This is the point that we have been trying to determine. Now, once you have located the point, it's very easy to go ahead and identify the different properties we want. The first one is the relative humidity, right? So we can see that these are the relative humidity lines, 60, 70, 80%, 90%, all the way. And the line that we are interested in, the point that we are interested in, it lies somewhere between this line, which corresponds to 70%, and this line here, which corresponds to 60% relative humidity. It's sort of more closer to the 70% value, and I mean, based on this, we can pick it up to be 67% here relative humidity, right? I mean, it's certainly higher than 65 for sure. So anything around 66 to 68 is still acceptable. Now about the humidity ratio, it's a pretty straightforward thing. You just need to draw a horizontal line. So you draw a straight horizontal line along this path, and we see that it ends up slightly higher than 0.018. Now this is already in terms of kilogram of water per kilogram of dry air, so we don't have to change anything. Now, to be more accurate, you can write it as 0.0181, but I mean 0.018 is also fine. We know it's slightly higher, that's why we are putting in this one. Okay, it could as well be 0.0182. All right, so that's the two of these done. Last is the mixture enthalpy. Now, mixture enthalpy is given on this axis right here. As you can see, the title is given, and these are the different lines of constant enthalpy. Okay, so we're looking at some point between 70 and 80, and if you look through this, we're looking at basically this point right here. If you just draw a straight constant enthalpy, if you draw a straight line parallel to one of the constant enthalpy lines, and when you count it out, it comes out to be 76 kilojoules per kilogram of dry air. So you, as an engineer, you should very well know how to make use of the psychrometric chart and read out these values from the psychrometric chart for calculating the enthalpy changes or the heat input or the cooling input that's required to change the temperature or the humidity of an air to the desired conditions. All right, so it's really important that you know how to make use of the psychrometric chart, and the pop quiz is going to contain at least 2 to 3 questions based on this. Okay, so make sure you understand this point. All right, so that's about the psychrometric chart. Next, we'll talk about air conditioning, what matters for air conditioning, and so on. All right, now that we have a good understanding of the moisture content within the air and how to deal with moisture, now let's try and understand its application. All right, so the ultimate goal is to condition the air or to make the air reach certain properties which make it uh, comfortable for us or which make it viable to be used in, let's say, the in workshops, for example, where you need to keep certain machines at a certain range of humidity and temperature. So when we talk about the modern air conditioning system, well, you can actually do a lot to the air that you get. You can heat it, cool it, humidify, dehumidify, even clean, or even sometimes remove the odor, remove the bad smells in the air. And basically what we are saying is that in the new air conditioning system, you can condition the air to whatever you want, right? Of course, each process is going to require some amount of energy input. So we're going to deal with the main component, which is about providing comfort, right? So you may need to heat the air, you may need to cool it, maybe humidify or dehumidify. So the other things such as cleaning, deodorizing, these are all things that are on top of it, right? Those are, let's say, good to have, but if you don't have them, it's not a deal breaker. The critical part of an air conditioning system is to ensure that um, uh, it brings the air to a condition which is comfortable for us. So now let's look at what does human comfort depend on. I've been talking so much about comfortable condition. So let's see what does human comfort depends on. It depends on 3 main factors. One is it depends on the dry bulb temperature or simply the temperature. It depends on the relative humidity and also the air velocity or air motion. Now, temperature is, of course, the most important factor. Most of us are comfortable when the temperature is between, let's say, 22 to 25 degrees Celsius. This is our most comfortable range. Anything higher or below this can cause discomfort to some people. Okay. Now, so that's the temperature range that we would want to maintain indoors, right? Or in the facility that you're trying to control the temperature. Now, in terms of relative humidity, right, the key point is we are not so much sensitive to absolute humidity. We don't have humidity ratio. We have rather relative humidity, which is phi. And the reason we care about relative humidity is because the relative humidity affects the way heat is dissipated from our body. Okay, we sort of reject heat from our body by evaporation of the sweats and so on. So you got to maintain the relative humidity in the appropriate range where the air is not too dry that our skin becomes dry and we become comfortable, or not so humid that it affects the way we are rejecting heat, the way our body is rejecting. Okay, so the relative humidity need to be kept somewhere in the 30 to 50% range. Anything higher than 50 is gonna cause less heat dissipation and can, of course, make us uncomfortable. Now, lastly, air motion is also important. You need to sort of move around the air within the room to replace the warm, moist air, which is around the body. And the typical ranges are about 15 meters per minute, right? This is the, say, the rule of thumb. You can move it around more or less somewhere this range. But of course, the most important part are here, the temperature and the relative humidity. How do you maintain this temperature? What do you need to do to get this temperature? What do you need to do to get the humidity? That's all what we'll be talking on for the next in the next few slides and even in the class on Sunday. Now, of course, there are other factors that play a role in our comfort levels, that such as air cleanliness, the noise, the heat transfer by radiation, and so on. But ultimately, when you're designing an air conditioning system, you got to care for the temperature and relative humidity. Okay. So what all can we do? All right. So if you want to maintain a living space such as your room, your house, or even the classroom or office space, or an industrial facility at some desired temperature and relative humidity, you need to make the air go through some processes, right? Which we typically call as, we sum them up and call it as air conditioning processes. Now, the processes could be simple heating, which means only raising the temperature, or simple cooling, meaning only lowering the temperature without doing anything to the humidity. Or it could also mean humidifying, meaning adding moisture, increasing the moisture content, or dehumidifying, again, removing moisture content. Now, the beauty of the psychrometric chart is that it shows up all these processes in very simple plot. So if you're just dealing with simple heating, then it's just a red line, right, as shown here. It's just a red line, red horizontal line, where the humidity ratio remains constant because we're not playing anything with the humidity. We're just increasing the temperature. If you are just cooling it, meaning simple cooling, without playing with the humidity, it's this line to the left, just a straight horizontal line to the left. Same way, if you are just humidifying it, it's a line to the top, the green line to the top as shown here. And if you're dehumidifying it while maintaining the same dry bulb temperature, it's just a line to the bottom, okay? Only the humidity ratio changes, nothing else. So these are the four basic processes. Of course, we can use combinations of them. And the two combinations that are used very commonly are heating with humidification, as shown here in this red line, and cooling with dehumidification. Now, there is an obvious reason why we would want to heat and humidify, or cool and dehumidify, and it simply comes from the fact that the air around us, or the air in the environment, is typically cold and dry in winters. Okay, so you got to heat up the air to take care of the temperature requirement, but you also need to increase its relative humidity or humidify it so as to keep us comfortable in terms of avoiding the dryness of the air, which can make our skin dry, which can cause irritation or allergies to a lot of people. On the other hand, in summer, the air around us is hot and humid. Okay, now it's relatively humid even in most places, right? So in this sort of a condition, you would want to cool down the temperature, reduce the temperature for sure, right? You want to bring down the temperature, but also at the same time, you got to bring down the relative humidity. We want to keep relative humidity somewhere, let's say about 50%, plus or minus. 50% is a good value to keep it, but anywhere in the 30 to 50% range works very well for us. What if the air is already in this range? Well, if you heat it up and the relative humidity is still thereabouts, you don't have to do anything else, right? So the cooling and dehumidification, or heating and humidification, are processes which are needed in some cases, not always. Okay, and we'll see how each one of these steps is implemented and what it means for the energy balance. So when we talk about air conditioning processes in general, we can simply model them as steady flow processes, right? And we can then apply the usual mass and energy balances. Okay, so for a steady flow system, we know that the mass in has to be equal to the mass out. So we break it down into the two components of moisture, which are dry air and water vapor. So you can write the mass balance for air and as well as the mass balance for water. As we've seen before, we would like to replace the mass flow rate for water with mass flow rate for air times the humidity ratio. Okay, this is humidity ratio is known for almost all states. If it's not known, you can get it from the psychrometric chart, and the mass flow rate of dry air remains constant throughout. So this is rather another way of determining this. Okay, it's essentially the same thing, the mass balance, and what comes in has to go out, right? Both for dry air as well as for the water. Now, in terms of the energy balance, we can come up with this general energy balance equation where it talks about the different ways in which energy can come into the system, right? Heat in, work in, plus the flow work coming into the system, plus the usual terms for the energy going out of the system. Now, when we're talking about air conditioning systems, well, there's no work out, right? The work output is a zero. Now, there is, however, some amount of work input, which in the form of the work input required to keep the fan running. And why do we need the fan? Well, we need to keep moving the air. We said about at a rate of 15 meters per minute, right? So there is some amount of work input for the fan, but if you compare it to the other terms in this equation, the work input to the fan is negligible. So you can also bring it down to zero. Now, depending on what you're doing with the air, whether you're heating it or cooling it, we may have a Qn, right, or Qout. So let's say if you're heating the air, so then you just need to add heat into the system, right? Our system now is composed of moist air. Moist air is the system. So of course, if you need to increase its temperature, you got to provide some heat input. Okay, Qn needs to be provided. So there is going to be Qn. There will not be any Qout, of course. So there will be Qn plus the mass flow rate times the enthalpy of the air coming in, dry air plus the water vapor. That's going to be equal to the mass flow rate times the enthalpy of the air going out, both the dry air and the water vapor. Now here we have written this separately, but in the psychrometric chart, we have the enthalpy for the moisture already given. So if you want to use this equation with the psychrometric chart, we can sort of rewrite it in this format where we are taking the mass flow rate of the dry air common, and then you have H out minus Hn, where H refers to the mixture enthalpy per unit mass of dry air. Okay, so this is simply HA plus omega times HW. Now, of course, if you're doing, if you need to cool down the air, that means the air needs to reject heat. In that case, we'll have Q out, and Q out would simply be equal to m dot A times Hn minus H out, where again the enthalpy here is the mixture enthalpy that we're talking about. Okay, mixture enthalpy per unit mass of dry air. Now let's deal with simple heating and simple cooling processes. Now, whenever we say simple heating or simple cooling, whenever you see this word simple on top of it, or simply when you say heating or cooling without any humidification part, we are talking about a process where we are just playing around with the temperatures. The humidity ratio will remain constant. We are not doing anything to the humidity. So let's start with the heating process. Now, heating process is something that we use very frequently in winter, and a lot of our residential heating systems in Saudi Arabia, they consist of an electric resistance heater. In some other parts of the world, they use they burn fuel, either gas or oil, to heat up the air, and the air in the systems simply gets heated, right? Its dry bulb temperature increases without causing any change in omega. So omega 1 is equal to omega 2, right? Inlet is equal to omega at the inlet is equal to omega at the outlet. So if you're looking at a duct like this, as shown here, so the air enters at some temperature and relative humidity and humidity ratio. It goes through these coils, get heated, right? That's the Qn coming into the system. Our system is air now, remember. And then it comes out at a temperature which is higher than the inlet temperature. T2 is greater than T1. And omega 2 is exactly equal to omega 1, okay? So it just comes out at a higher temperature. Now, when we're dealing with the cooling process or the simple cooling, well, we are essentially doing the same thing, right? So instead of the hot heating coils, you have the cooling coils, and you could pass a refrigerant through the coils, or you could even pass chilled water through the coils. When we talk about industrial or large-scale units, chilled water is the preferred way to cool the air, right? So if you look at our university in KFUPM and other places, chilled water is what's normally used for providing the cooling effect. Now, when we talk about whether it's cooling or heating without any humidification, well, we already discussed that the humidity ratio is going to remain constant, right? But it's important to note that the relative humidity changes. And why does the phi change? Well, phi changes because we're playing around with the dry bulb temperature, okay? So we're keeping the amount of humidity constant, so mass of vapor is remaining constant, but the maximum mass that the air can hold, mg, is something that we are increasing or decreasing based on the temperatures. All right. So if you're cooling an air, right, simple cooling, it shows up as a horizontal line on this, like the one shown here. You're cooling it from 30 degrees to 12 degrees Celsius. The omega is absolutely constant, but what's happening is, as we are decreasing the temperature, okay, so if you write this in terms of, phi, if you write it in terms of partial pressures, PV by PG, we're sort of decreasing the PG simply because the saturation pressure decreases with decrease in temperature, okay? So you're decreasing PG while keeping the PV constant. So what's going to happen? Well, phi is going to increase, and that's what we see here. The relative humidity increases as we cool it. Okay, we're not doing anything else. We're just cooling it. So you got to be careful that the eventual relative humidity is still within the range when you send it to the air, to the room or to the space that you want to provide cooling. All right. Now coming back, we said simple heating and cooling are going to appear as a horizontal line on our psychrometric chart, and that's why psychrometric chart is pretty useful. And now it's time to write the energy balance for this. So when we're talking about energy balance, we always, of course, also talk about the mass balance. The mass balance is going to be very straightforward. It's the mass of dry air is not changing. The mass of water vapor is not changing. So you can simply write it in terms of the omega. In terms of the energy balance, depending on what's heating or depending on the heating or cooling, you could have Q in or Q out, and it's going to be equal to the mass flow rate of dry air times the change in the mixture enthalpy. All right. What is this enthalpy? As we just discussed before, it's HA plus omega times HV. Okay, just like the one we discussed in the last slide. All right. Now that we have discussed about simple heating and cooling processes, let's go and deal with heating with humidification. Now, why do we need heating with humidification? Well, as I mentioned before, when you're dealing with winter air, so in winter, the temperature is low and it's also contains less moisture. So it's basically cold and dry, okay? And for the cold part, you can take care of it by doing the simple heating process, right? Make it pass through heating coils. That does the job. But once you heat it up, the problem is that the relative humidity further reduces. Why is it reducing? Well, relative humidity is again can be written as PV by PG. Okay, when you increase the temperature, PG is increasing while the numerator is remaining constant. So that means phi reduces, and this is something that's already low to start off with. Okay, so therefore we need to humidify it. We need to add some amount of moisture. So the question is, how do you add the moisture? Well, it's a pretty simple process. If you want to achieve heating with humidification, the way to do it is first you make the air go through the heating coils to achieve the simple heating part, just like we did in the previous slide. And once it's at state 2 at a higher temperature and lower relative humidity, then you send it through a humidifier. Now in the humidification section, you need to add moisture. Okay, you can add it either by adding steam in the form of steam, or you could also spray liquid water, liquid droplets. Depending on what you do, the final temperature is going to be different. Okay, so but ultimately you just have to add more moisture. All right. Now, in really simple terms, if you want to, I mean, if you imagine imagine you're in your room and you don't have any sort of humidifier, right? You could simply add more moisture to the air content within your room by keeping water in an open container. So the water is going to get evaporated. Of course, the rate is going to be slow, but it adds moisture, right? And that's ultimately what we want to add. So in industrial cases or in large systems, you don't have really time to wait for the water to evaporate. So what you do is you sort of just inject steam or liquid water into the stream, right? Into the stream that's coming in, into the airstream that's coming in. Now, let's break it down into two parts. The process 1 to 2, where simple heating happens. The mass and the water balance is pretty similar to what we discussed before. And the energy balance is also exactly the same. You're just heating it up. So you need to provide some heat input, and that's going to show up as increase in the enthalpy for the mixture, right? You're going from 1 to 2. It's a horizontal line, increase in the dry bulb temperature and decrease in the relative humidity. Now at state 2, it's going to be smaller than 30%. Okay, we don't know how much, but surely it's going to be smaller than 30%. Now that's the first part done. What do we need to do from 2 to 3? We just need to add moisture. Okay, so if you, let's say, inject steam through this humidifier, then your steam is something that comes in at a much higher temperature. So you're going to see heating plus humidification. There will be small increase in temperature. It went from 22 to 25, right? But the main part here is to add moisture content. So the main part would be increase in the moisture level or increase in the omega level or also the phi. Okay. Now increase in omega does happen, although we don't really care about it. What we care about is the increase in the relative humidity. We want it to be at a comfortable level. So when you write the mass balance now, it's going to appear as mass flow rate of water at the inlet at state 2, for example, plus the amount of water that you need to add through the humidifier. That's going to equal to the water content of the moist air that's coming out at the end of the humidifier. All right. So depending on what you want the state 3 to be, you can decide how much water to add. Okay, you can decide the mass flow rate of water that needs to be there, that needs to be sprayed to get you the right moisture content at the end of the entire process. So that's it for now. We will continue on Sunday from here. We're going to talk about cooling plus dehumidification and also solve a problem based on that. For now, I strongly encourage you to go through this example 12.2, which deals with heating and humidification, and see for yourself how these different concepts apply in reality. All right, and this is the material for the pop quiz. You're going to have 2 pop quizzes, which I'm going to upload probably within the next 10-15 minutes. So good luck. And as I mentioned before, you can attempt the quizzes unlimited times, right? You have 2 days. You can try them out as many times as you like. So that's it for me. See you on Sunday. Have a nice weekend.